You're listening to the Jefferson Exchange. I'm Mike Green. We often think of global warming as a gradual, uniform heating of the Earth. But oceanographers and climate scientists have long known that Earth has a highly complex climate plumbing system. At the heart of this system is a massive network of currents that shape regional climates. And for more than 11,000 years, this system of currents has been remarkably strong and stable. But many scientists believe human-driven climate change is starting to disrupt this flow. A new research study published in Nature Geoscience revealed that this Atlantic Ocean system of currents acts kind of like a control knob. When it weakens, the impact on the Earth's temperatures could be far more severe than previously understood. Here to talk about this groundbreaking discovery is the study's lead author, Christo Buizert. He's an associate professor of paleoclimate at Oregon State University. Professor, welcome to the Exchange.
Thank you, Mike. It's a pleasure to be here.
Well, let's start with the description of your work and what led you to it. What is a paleoclimate scientist?
Oh, good question. As you're starting in your introduction, climate is changing right now. And one way to understand that is by using complex computer models. And they're very good at predicting what might happen in the future. But a different route of understanding those changes is actually by looking in the past. So our Earth's climate has always been changing, and we can use those natural changes of our climate as a way to better understand our planet. You can think of it as Mother Nature's own little experiments. By studying those past experiments, we can understand how sensitive our planet is, how the different parts of the planet work together, and by understanding that, we can better project what might happen in the future.
Okay,
so it's basically studying climate change in the past.
Okay, so paleontologists is kind of part of what you do.
Paleontology mostly studies past evolution and past animals, past life. What we study more is the physical environment that life lived in, right? So we're thinking about the ice ages, for example. It's a good example. So, for example, for your listeners here in the Pacific Northwest, right now, most of the Northwest is ice-free. During the last ice age, about 20,000 years ago, the ice covered all the way down to Tacoma. And that's a massive climate change. And those type of changes are massive and global. And those are sort of examples that we can learn from to understand how our climate system works. So the study that we're talking about today actually takes place during this ice age period.
Well, your study describes a current system in the Atlantic Ocean as a heat valve or a control knob. Mm-hmm. Help us understand what your research discovered.
Yeah. So we're talking about this current in the Atlantic, which is the AMOC, the Atlantic Meridional Overturning Circulation. And this is a really important part of the global ocean circulation. It distributes heat, it distributes nutrients. So it's really important for fisheries, for example, but also for the temperatures around the world, in Europe, for example. And as you mentioned correctly in your introduction, there's some fear now among researchers that this current, this AMOC current, may be weakening into the future.
Okay, so let's go back really slow with AMOC. AMOC is an acronym.
That's correct.
What does this stand for again?
Yeah, sorry, I went a little fast there. So AMOC is an acronym that stands for the Atlantic Meridional Overturning Circulation. So the Atlantic part is just the Atlantic Ocean that you're familiar with. Meridional means it goes from north to south. The overturning circulation is just the word that oceanographers use to describe the really large-scale circulation of the ocean. So the circulation that happens on the scale of the entire planet. And this AMOC, the part of the AMOC that most people are familiar with is the Gulf Stream. My in-laws live in South Carolina. When you go swimming there, it's very different from our very own Pacific Ocean off the Oregon coast. It's very nice and warm. It's that warm ocean current, the Gulf Stream, that brings warm waters from the Atlantic tropics all the way to the north, where it warms Europe, for example. And then what happens when that warm water goes all the way to the north, it cools down, particularly in the winter. And when it cools down, it becomes really dense and heavy, and it allows it to sink down to the bottom, and then it flows back to the south. So that's what that current does. It brings warm water to the north at the surface, it sinks, and then the cold water moves back down to the south. That's what the AMOC does in our climate system.
Gotcha. That was a really good explanation. Thank you. Now, your team avoided relying solely on computer simulations. Instead, you looked back at history, like you said, but you did something that's unusual, I guess. You extracted ice cores from Greenland and Antarctica.
Yeah, that's right. Um, like I mentioned, Earth's climate has always been changing, and we can use these past natural changes to better understand what might happen in the future as humans are changing the climate. So, when we're talking about the weakening of this current, the weakening of this AMOC current, we have about 25 examples of that happening completely naturally during the last ice age. So, what we did for our study, we looked back in time using our ice cores and looked at these natural examples of time periods where we know that this AMOC current weakened naturally, and used that to better understand what might happen, what happens to the global climate, and what might happen in the future. To be more specific, when we want to understand these abrupt changes to this AMOC current, we go to Greenland. Greenland is sitting right there in the North Atlantic, so it's extremely sensitive to what this current is doing. You can think of Greenland a little bit as I think most people are familiar with tree rings. A tree grows a new ring of wood every year. A similar thing happens in Greenland. Every year there's a fresh layer of snow, and in the interior it is so cold that this snow never melts. So this snow has been piling up for hundreds of thousands of years. In fact, the ice in Greenland is about 2 miles thick in the thickest places. So you can think of Greenland as a mountain made entirely of ice. So what sort of the teams that I'm a part of in our expeditions, we go to Greenland, we go to the interior right in the middle, and we drill an ice core from the top all the way down to the bottom. So basically, we have a 2 mile long stick of ice. And as we're drilling through all those layers that have been, deposited over these hundreds of thousands of years, and we can study those layers in great detail to understand how the climate of Greenland has changed. What we find is every time that this AMOC current weakens, we see a pretty abrupt and really extreme cooling in Greenland. And when I say fast, I mean 100 years, so by human standards, maybe not that fast. But when we're talking about geologic time, that's the blink of an eye. When I say large-scale cooling, we're talking about maybe 15 to 20 degrees Fahrenheit within 100 years. So that's a pretty extreme example of natural climate change.
Okay, so your team analyzed 25 instances of abrupt climate changes, right?
Well, yes, these are the events that we're studying. We didn't look at each one individual. We know about these data exist. That's sort of the observational evidence that we have that the AMOC weakened. What we did in this study is that we also combined it with those models, those climate models that you mentioned earlier. These are the models that scientists use to project what might happen in the future. So in my work, what we try to do is test those models. Here we have examples of climate change in the past, and we can use those to test how well these models perform. In this particular study, we looked at 3 different climate models that are able to simulate those natural fluctuations in the AMOC, these natural changes in the AMOC. And we find that the models are sort of, bang on with the observations. They do a fantastic job in simulating what we see in our ice cores. So that's why we trust these models, because they actually do such a good job of simulating what we see in our ice core records.
If you're just joining us, my guest is Christo Buizert, a paleoclimate professor at Oregon State University. He's the lead author of a new study that discovered a system of ocean currents in the Atlantic could act as a temperature thermostat for the regions all across the Earth. So, Professor, scientists have talked about what they call a thermobipolar seesaw. This idea that a weak AMOC, as you called it, simply shifts heat from the northern hemisphere to the southern hemisphere. But your research reframe that. How so?
Yeah, that's right. So we were just talking about those ice cores in Greenland and what they're showing us. The other place where we like to drill ice cores is in Antarctica at the South Pole, so the opposite end of the world. And we see a very clear impact of these changes in the AMOC all the way in Antarctica, right? So you're on the opposite side of the planet, and you can still see the impact of these events. And it's a little bit different in the sense that when we know that the AMOC was very strong, that's the times that Greenland was relatively warm. It's still, it's still Greenland, it's still frozen, but it was relatively warm. During those times when Greenland was warm, we see Antarctica is cooling gradually. At the same time, when Greenland is very cold and this current, this AMOC current is very weak, Greenland is cold, at those times we see Antarctica warming. And this pattern was known for, a decade or two now. And this was typically known as the bipolar seesaw, is the name people called it. So seesaw, right? So you think of the seesaw, one side goes up, the other side goes down. That was the idea. The idea here is that Greenland is warm, Antarctica is cold. Greenland is cold, Antarctica is warm. That was the seesaw idea. And so previously, people just assumed the heat was just moving back and forth, right? If the AMOC is strong, the heat goes to the north and the south cools, and the other way around. If the AMOC is no, I forgot. I lost my train of thought. But you get the point, right? So when the AMOC is strong, Greenland is warm, and the AMOC is weak, Greenland is cold, and that heat is sloshing back and forth between the hemispheres. What we found is, so when we looked at these computer models, these models that do such a good job of simulating the observations from both Greenland and Antarctica, these models are not just sloshing heat back and forth. What is really happening is the entire planet is warming up and cooling down. So when this AMOC is running strong, it's actually extracting heat from the entire ocean, not just taking some heat from the south. The global ocean is cooling down. On the other hand, when this AMOC is very weak, that heat is not going to the north, and so this heat just builds up in the entire ocean. So now the entire ocean gets warmer. And it's not just the ocean, it's actually the atmosphere works together with the ocean. So the ocean and the atmosphere are kind of working together to make sure that when this AMOC is weak, the entire planet is gaining more energy, more heat. And that's the concern that we have, right? As we're looking into the future and we're seeing that this AMOC might be weakening in the future, the implication there is, it means that the whole Earth would be gaining more heat. So the global warming that's already happening could be accelerated, maybe by up to 10 years or so.
And you believe that's due to human-caused activity?
So we know it's very obvious that the ones that we studied happened in the past. It's very obvious that those happened naturally. However, by looking in the past, we also know these natural changes happen only during ice ages. Right now, we're in a warmer climate in between ice ages. And during those climates, the AMOC has always been very stable. Every time we can find a climate that's similar to ours right now, this AMOC is steady and stable. For the last 12,000 years, this AMOC has been stable. Right now, we're worried it's weakening. The reason we attribute this to humans is actually the physics of it all. So the physics of it are relatively straightforward in the sense that I told you earlier, this AMOC current is warm water moving north, cooling down and sinking and flowing back down. That's sort of the mechanism that keeps the AMOC going. For water to sink, you need two things. It needs to be cold or it needs to be very salty. Those are the two things that make water very heavy or very dense. What's happening because of global warming is now this surface ocean is warming up. So this warmer water has a harder time sinking to the bottom. The other thing that's happening is that Greenland ice sheet we talked about earlier. It's a giant mountain of ice, right? A massive ice cube that's sitting right there. We know that Greenland is now losing mass. So it's melting because of the warming, slowly, but still it's melting. And all that fresh water that runs into the North Atlantic. So that water in the North Atlantic is becoming both warmer and fresher. Those are the two things that make it want to stick to the surface, right? Those are two things that stop it from sinking. So because of those two mechanisms, we're expecting this AMOC to weaken in the future. And it's very robust in climate models. If you ask 10 models what's going to happen with this AMOC in the future, probably all 10 of them would tell you that it's going to weaken. The question is how much and how fast.
Okay, we have about 30 seconds left. Your study does offer a silver lining. What is it?
Well, the silver lining here is I mentioned earlier that whenever in our observations of the past, whenever the climate is warmer, this AMOC tends to be more stable. Some scientists have suggested that we might be looking at one of those catastrophic, irreversible collapses in the next 50 years or so. But from our research, it seems that in a warmer climate, actually overall, the AMOC should be more stable. That means it might weaken a little bit, but we predict it will recover. So it will not collapse forever. It will just weaken for a shorter period of time and then recover afterwards.
Okay, let's hope you're right. Thanks so much, Professor.
It was a pleasure being here, Mike.